Okay, just going to take a minute to talk again about what we discussed in the lecture, which is this theorem, which is called the work-kinetic energy theorem. Of course, we introduced in the lecture the concepts of energy. Here we have the change in kinetic energy on the left-hand side, and the concept of work. And what we defined work as was the energy that is imparted to a body via a force. So here we've got the kind of prototypical example of a person pushing a box across the floor. And the idea is that the person in applying this force is doing work on the box. So quite often you'll hear this language of doing work on a body or on a particle or on a box like this. So the force is what does the work. Okay. So the work is defined as the force dot product with the distance or the displacement. So by pushing the box, say from this position to some new position over here, we cover some distance d in this direction. And because we're applying the force in the same direction as the displacement, the work then just becomes simply the product of the force times the distance. Or the other way to think about this is if the box is actually moving in this direction and I'm trying to stop it sliding by pushing on it, the displacement of the box will actually be in this direction. The force is in the opposite direction. And this then means that the dot product will actually have a minus sign in it because it's the nature of the dot product, as we discussed in the lectures. And so the amount of work then will be negative. So I actually do negative work, which means that I reduce the kinetic energy. So it's initially moving, I push back on it to stop it. So I reduce the kinetic energy. Whereas in this first example, I push it and I move it over here and I actually increase the kinetic energy because the velocity increases as I move over here. So this is the key idea, the key concept to get across is by doing work, which means applying forces and moving objects, we actually change the kinetic energy of the system. And there's just two examples that I wanted to give, one of which already kind of covered in the lecture, which is the idea of pushing a box on the floor. And so we're applying some force to move it in this direction, but it actually moves at some constant speed. So let's say that v is just equal to, well, we'll just say v is v and a is 0. So if a is 0, what that means is that the change in kinetic energy must be 0, okay? Because the velocity doesn't change. Another, you can say that v is equal to v naught, i.e. whatever our initial speed is remains the speed, okay? And if that's the case, then the change in kinetic energy is 0, because of course kinetic energy is just half the mass times the velocity squared. So if the velocity stays the same, the kinetic energy change stays the same. And that means that no work is done by the kinetic energy theorem. So if that's the case, then how come it costs us effort to push this box across the floor? And of course, the answer is that there is some resisting force here, which is, say, the force due to friction. And what that means is that these two forces are in balance. And of course, we know from Newton's laws that must be the case, because if I have a net force, let's write net here, then it must cause an acceleration. But here we're told the acceleration is 0. If the acceleration is 0, that must mean that we've got a 0 net force. And so in this example, then F, the force that I'm applying to move the box, must be equal and opposite to the frictional force. So these two things cancel each other out. And we end up with 0 net force, 0 acceleration, and therefore the work done is 0. So that's the first little example, just to cover the nuances of the work energy theorem. The other example is of moving objects under gravity. We'll actually do a whole lecture on this next week. But imagine that we are actually raising some object, or in fact, let's imagine that we're throwing it upwards, okay? So we throw this box upwards. Well, after we sort of release the box, it's traveling upwards like this. So the velocity is directed up there like that. What forces are acting on the box? Well, gravity is acting. So we have this force due to gravity, the weight of the box, which is acting in this downward direction. And so what that means is that the gravity, so the Earth, which is exerting that gravity, is doing work. Okay, well, what is the work? Well, the work done is going to be equal to the dot product between the displacement, which is in this direction. Okay, so velocity is in this direction, displacement is going to be in this direction. So we're moving our box up to some new position. So this is our displacement like this. The work done is going to be equal to our dot product between the force and displacement. Well, the force is in this downward direction, so I have minus mg, and the displacement is in this upward direction. So we'll have however high that moves up. But they're directed in this opposite to each other, which is where this minus sign comes from. So what that means is the work done by gravity is negative, and it reduces the kinetic energy by this precise amount, mgd. Okay. Now, we don't know how fast the object is moving initially. We don't know for sure that the object comes to rest or anything like that. But let's imagine that we throw it up and we kind of measure now the energy at the topmost point of this motion. Well, at the top of the motion, the kinetic energy is actually zero. So whatever kinetic energy our object had to begin with has now disappeared when it reaches this point. And what we discussed in the lecture was this idea of the conservation of energy. And so the work done by the force of gravity here, this minus mgd, this is the reduction in the kinetic energy. So we reduce the kinetic energy by this amount. But as we discussed in the lecture, that energy doesn't disappear. It has to go somewhere. And this is the conservation of energy. That's the key idea there. And so where does that energy go? Well, if you're familiar at all with gravitation, you'll know that this energy corresponds to the gain in potential energy or gravitational potential energy. So whatever we lose in kinetic energy in rising through this distance, we actually gain in potential energy. And of course, then when it falls back down again, that potential energy is transferred into kinetic energy. And again, we'll find that in that case, then the displacement will be, so this would be our second displacement for the second part of the motion. It moves in this direction. Now these two things are aligned. Well, the work done by gravity will then be positive, and that will then increase our kinetic energy by this same amount, mgd, and there it's converting the gravitational potential energy into kinetic energy. So this is just a couple of examples to kind of show how this work kinetic energy theorem works.